In the last video, we learned about sampling in general, and we learned that we can sample analog time continuous signals and obtain a time discrete signal. But can we sample any signal without any restrictions? No, we can't, and we will learn about the restrictions in this video. Further reading on this topic is in the lecture notes in chapter 4.1.2, and the restriction which we are gonna learn about is the sampling theorem. So, and here's an example that illustrates the restriction of sampling. So we have two signals, signal 1 and signal 2, and both signals are described here in this diagram, and we choose a sampling period TS. And now we have a very special condition. We sample both signals with the same sampling period, and we obtain for both signals the same sampled impulse series here, as you can see. So if we sample the signal at time instance 0, both signals do have the same value. Same goes for the next sampling time and for each other sampling times. So the sampled signal, our time discrete but still value continuous signal, will be the same for both input signals, and that is the problem that we are going to discuss here. What is the reason of this phenomenon? So we now switch to the frequency domain, and let's consider one signal. So for now we just neglect the second signal, just take one signal. Here's the spectrum of the signal, and here the spectrum is not equal for for the positive and for the negative half plane. So here we might have sampled a complex valued signal where the symmetry rules do not apply. But however, this is not important here. So what is the consequence of our sampling? So in the time domain, we learned that the sampled signal is just the input signal, the analog input signal, multiplied with the Dirac comp. And now we switch to the frequency domain, and for this we have to look at the Fourier transform of the Dirac comp. To get all the mathematical background, please read the lecture notes. Everything is written there. Here are just the solutions of the Fourier transform. So the Fourier transform of our Dirac comp itself is a Dirac comp. The proof is in the lecture notes, so refer to the lecture notes if you want more background information. And so here we have the Fourier transform of our Dirac comp, which itself is a Dirac comp. It has also a periodicity, which is the sampling frequency here as an angular frequency, you know. Ooh. Of course, sampling time. Yeah. And now as we switch to the frequency domain, our multiplication becomes an convolution. Yeah. This is very important. And now what is the practical consequence of the convolution? Our original spectrum shows up again, but it is repeated. It is repeated indefinitely times. Here, it just depict the first 5 repetitions, but here it goes on, and here too. So this is the practical consequence of the convolution with the direct comp. So the signal goes here, and over the second pulse in the direct comp here, and so on. Yeah. So this is quite fine for one signal, but now let's have a look at what happens if another signal comes in. So this is our original problem, which we have discussed in the first slide. So now we have the spectrum of our green signal. Here again, this is just an illustration. It's not the real Fourier transform of the green time domain signal. This is just to illustrate the problem. And now we have a second signal which produces the black spectrum here. Here is a special point in the frequency domain. It is the half of the sampling frequency of the angular sampling frequency in this case. This is an important point, as we will later see. It is here, it is in the middle of the pulses in the direct comp. And now we just convolute the frequency domain signals with the direct comp, and now we see what happens. So the green spectrum is convoluted and shows up here and here and so on. And now the second spectrum is also convoluted. So let's take this pulse first and consider this part of the black spectrum. It shows up here, and the negative part shows up here. Now take the other pulse. Now this the positive part of the spectrum goes here, and the negative part of the spectrum goes here, and so on. This also indefinitely continues. And now we see what the matter here. We have overlapping spectra. So the spectrum of the sampled signals of both the green and the black signals are equal. And this is what we see here in our sampled signal, that this is equal here. So what is the matter? Why do we observe this phenomena? It is the Shannon-Nyquist sampling theorem. The Shannon-Nyquist sampling theorem says that the maximum frequency which is allowed to be contained in the original signal must be less or equal than half of the sampling frequency here. So maximum frequency in the signal less or equal than half of the sampling frequency. And now we see why these points are so important because we see that the black signal here, the black signal violates the Shannon-Nyquist something theorem. And the effect which is caused by violating the Shannon-Nyquist something theorem is called allealizing. So as a consequence, we as digital communication engineers have to care about fulfilling the Shannon-Nyquist something theorem. So this is why before sampling a signal, we need to apply a low-pass filter which restricts the signal energy to just a certain band. So everything outside the band is just thrown away, and now we only have parts of the signal which fulfill the Shannon-Nyquist something theorem. The rationale behind this is, as we deal with a real system, we might get some signals which exceed the Shannon-Nyquist sampling theorem, like this, and so we have to filter out the interesting part here. And if we forget about low-pass filtering the signal, then we will see allealizing effects in the sampled output signal. Here at this point, so the signals just overlap and will disturb the sampled signal. So low-pass filtering is important each time when you do sample an analog signal. And another point where the Shannon-Nyquist sampling theorem is important is reconstruction. So please read the chapter 4.1.2, which also considers reconstruction. But in general, it is about transforming a signal back to the time continuous domain. And imagine that you have a sampled signal and you want to reconstruct it, so return to the time continuous domain. Then you would just connect the bubbles here. But if you have violated the Shannon-Nyquist something theorem, you will not be able to reconstruct the original signal, which would look like this. So this is not possible. And this is the second point why it is important to obey the Nyquist Shannon something theorem.